Great. Thank you, Dan, for inviting me, and thank you for everybody who's here. I see there's a lot of people. So I also see Doug's here. Doug. So this picture in the background is a picture Doug sent me at some point. So I liked it, so I'm using it for my background slides. All right. So this is the first part of a 4-hour mini course, which is meant as an introduction to chromatic homotopy theory. And by an introduction, I really mean an introduction. So the outline for the course, well, there's the construction cone here because I'm still making the other lectures, so things might move around, but roughly in the first lecture, so today I'm going to talk about spectra and localization. So there's going to be little about chromatic homotopy theory today, but I just hope to get everybody on the same page. In the next lecture, I'll talk about complex orientation and introduce the Moravec theories. So this lecture is going to be like everything about MU, the complex Cobordism spectrum. In the third lecture, I hope to get to the chromatic filtrations. So this will involve things like the nilpotence theorems, the fixed category theorems, and also mention the conjectures probably in this lecture. And finally, I'm going to talk about, in the last lecture, I'm going to talk about Moravec theory and the stabilizer group. So this will be something like KN local homotopy theory. I know that probably doesn't make sense right now, but by then it should. Okay. All right. So for today, so these are the topics that I will hope to cover today. So the last bit here is the motivation. And I decided that I would start, so this is like the setup. This is the background that puts us all on the same page. And I decided that I would start by the setup so that I could be less wishy-washy with the motivation. So I could make more precise what I mean when I get to what is chromatic homotopy theory. All right, so I want to start somewhere where there's a good chance that everybody attending sort of can meet me. And so if you've taken an advanced course in algebraic topology, then you've heard about cohomology with, ordinary cohomology with coefficients in G. So I'm a abelian group, okay? So this is an abelian group. So what's cohomology? It's a contravariant functor from, so this here is based CW complexes. And the op is the part where it says that it's a contravariant functor, so it switches arrow. So it goes from the category of base CW complexes to the category of abelian groups. So ordinary cohomology satisfies a list of axioms. So for example, if it's homotopy invariant, if two maps are homotopic, then they induce the same map on cohomology. So there are other axioms, so I'm just putting them there. You should sort of, if you've seen this, you should glance them and recognize this list. But let me focus on the suspension isomorphism. So one of the axioms for ordinary cohomology is that there's a natural transformation that gives an isomorphism between the nth cohomology of a space X and the n plus first cohomology of the suspension of X. And I should have said, here I'm talking about reduced cohomology. Okay. All right, so this suspension isomorphism is the isomorphism is part of the data. And so depending on the course you took, you might have seen that cohomology is actually a representable functor. Okay? So you can describe the nth cohomology group of X by the based homotopy classes of maps from X into a space KGN. So KGN is an Eilenberg-MacLane space. And its defining property is that it has one homotopy group in degree. And so we'll see a bit in two slides. So the suspension isomorphism is actually, so it can be encoded in the data that KGN is homotopy equivalent or weakly equivalent to the loops on a KGN plus 1. Okay, so just picking such an equivalence gives you a choice for this natural isomorphism. So that's part of the data for the suspension isomorphism. All right, so we're not going to talk about ordinary cohomology theory so much. So what we're going to talk about in this whole lecture series about generalized cohomology theories. So if you take these axioms, you can what you get is something that people call the Eilenberg-Steenrod axioms, okay, for generalized reduced cohomology theory. However, there's one axiom, the last one, I didn't really mention it, but the dimension axiom, this one we don't ask. In fact, if you have a contravariant functor from base topological spaces to abelian groups that satisfy all of these n, this number 5, then you would just recover the setup that you had before. So you just recover ordinary cohomology. So scratch that one, but keep the other ones, and that's the definition of generalized reduced cohomology theory. Okay. So now maybe the reduced bothers you. If it does, don't worry. So you just pass from reduced to unreduced by the unreduced cohomology of a CW complex is the reduced cohomology of the space X, and this just means here you take X and you adjoin a disjoint base point. Okay? So those are the axioms, and you might ask, okay, so on the previous slide at the end I said, well, ordinary cohomology is representable. So what about these? And the fact that these are all representable is a theorem called the Brown representability theorem. So if E is a cohomology theory, then there's going to be a sequence of spaces, En. So for ordinary homology, these were these KGNs, these Eilenberg-MacLane spaces, but in general, they're just base spaces, together with the data of a weak equivalence from En to the loops on En plus 1. Okay? So for any cohomology theory, there's such a sequence, and that sequence represents your cohomology theory. So the nth cohomology of X is going to be base homotopy classes of maps from X to the nth space of the sequence. So this here, so this map is supposed to have something to do with the suspension isomorphism. I mentioned that before. So let's see that now. So there's an adjunction between the loops functor and the suspension functor. So the loops functor, this is just, this is just base maps from S1 into the space Y, and this is the smash product of X with S1. Okay. So from that adjunction, you get that homotopy classes of maps from X to the loops on Y is isomorphic to maps from the suspension of X to Y. And using this, we get the suspension isomorphism. So suppose that you have your generalized cohomology theory, the nth cohomology of X is the base map from X to En. So you can post-compose with the structure, this structure map, this weak equivalence, and because it's a weak equivalence and X is a CW complex, you get an isomorphism between this group and this group. Now you use the adjunction, okay? And then you get that that thing was isomorphic to the nth plus first cohomology group of the suspension of X. So these are the generalized cohomology. They're representable by these sequences and these structure maps. But these objects beg to be inside a category. So that category, that's what people call spectra. So that's the category of spectra. So there's a lot of different ways to describe this category. So I've picked one and I'm gonna just go with it. So you might have other preferred approaches, that's okay. So the objects in the category spectra, so I wrote omega spectra here because in the literature that's often what these are called, okay? But I'll just call them spectra. So a spectrum E is gonna be a sequence of base spaces, just like before, together with these weak equivalences, these structure maps. Okay, so what are gonna be the morphisms in this category? So if I have two spectrum, a map is going to be a sequence of, continuous spaced maps of topological spaces, and such that this diagram here commutes. Okay, so in some ways it's like you had these structure maps, you had these spaces, and the maps are what they had to do. Okay, so they're maps within the level that sort of work well with the data that you have. So I'll denote this category by spectra, SP. Okay. So now, often when you're sort of looking at cohomology theories or you're building these things, you'll come up with a sequence of spaces and you'll have these structure maps, but there won't be necessarily weak equivalence. It turns out you can always sort of change things so that they end up being weak equivalences. In the case where the structure maps you have, which were not necessarily weak equivalences, were actually inclusions, then this is easy to describe. So if you have a sequence, but it's not quite a spectrum, then you can sort of upgrade it. So this LE here, so its end space is going to be, you take the colimit of these gadgets here. So you have these structure map between. So you have like E0 goes to loops E1, goes to loops 2, E2, and you keep going. So you can take the colimit here. And so that would, the colimit of what I wrote here would be the zeroth space of the new spectrum. And this new spectrum, you call it the spectrification. Okay? And you do something similar with the structure map. So I'm going to go and give you a bunch of examples, but I won't, but they won't all obviously have these structure maps be weak equivalences. Okay? But we can just always turn them into them. Okay. All right, so what are going to be the key examples for us? So first, let's just touch base with what we had before. So ordinary cohomology theory of coefficients in G, we already saw. So it's represented by the n space is a KGN. And the structure maps are a choice of weak equivalences between these two Evan-Vernick lane spaces. So the next example, and these examples are going to come up in the rest of the lectures. So the next example is complex K theory. So Bott periodicity tells us that the loops on the unitary group, so U is the union of all the UNs, all of the unitary groups. Okay? So if you take the loops on that, that's homotopy, that's weakly equivalent to Z times BU. And then if you do that again, you take the loops on that, then you get U back. So that's Bott periodicity. And so this sort of tells you, oh, it looks like it's going to fit right into a spectrum. And complex K theory is represented by the sequence, which you start with Z times BU, U, Z times BU, U, Z times BU, and so on. And the structure maps are coming from Bott periodicity. So another type of example that's going to be important are suspension spectra. So it turns out that if you have a base space, then you can turn it into a spectrum. And so we're going to always, so we have this category of spectra, we're actually going to think of spaces as living inside it. Okay, so it's like an enhancement of spaces. So for a base space X, the suspension spectrum is going to be the spectrification. So we're going to use that functor L that I had before of the following sequence. So the n space is the n suspension of X. The structure maps, so I need a map from sigma n to the loops on sigma n plus 1. Well, remember our adjunction, so a map into the loops is the same as a map from the suspension, and so we're going to use omega n to be the adjoint to just the identity map. So sigma n is smashing x n times with s1, so if you do it one more time, that's the same as having done. So we're often going to write just X for sigma infinity X. So remember, sigma infinity X is like the spectrum associated to a space, but sometimes we just call it X. We drop this heavy notation. And one of the most important spectrum is the sphere spectrum, and I'll write it as 0 to mean the suspension spectrum of the, of just 2 points. So if there is space for confusion, then I'll use this notation, but otherwise I'll stick to S0. All right. So these are the first 3 examples. So there's one more example that's going to come up, It's the complex cobordism spectrum. So there's complex cobordism is going to play an important role. So you might, so usually, so I've talked about cohomology theory, but people are more familiar with the homology. So for example, the homology of a point, the MU homology of a point, is just going to be cobordism classes of manifold with an almost complex structure on their tangent space. Okay? So that's something, you know, like it's the usual pairs of pants story. Those weren't pants. Okay. The usual pants story. So that's that usually use that story to describe the homology theory of MU. But okay, so I'll go straight at MU from the spectrum perspective. So MU again is going to be the spectrification. So we're going to use this functor L that I talked before, and we're going to use the following sequence. So it's going to be MU1, sigma MU1, MU2, sigma MU2. What are these? So MUN is a Thom space. Okay, so it's the Thom space of the following vector bundle. So BUN, so a model for BUN is the Grassmannian of n plane and C infinity. So that's really just a colimit, but let's, I won't go there. So basically you have an n plane inside some colimit of CNs or CNs, and then to the plane, so L maybe is your plane, or maybe P is a better word. So P, you can just, so you can look at the plane and you send it to its equivalence class, like, or not its equivalent class. So the plane is, so sorry, the points here are planes, and the bundle, the fibers, are the vectors in that plane. Okay, so now you take the Thom space, which is, so you take the one-point compactification of all the fibers, and then, you know, you take all the point at infinity and you crush them to a point. Okay, so that's MUN. Now, UN, there's a map from UN to UN plus 1. So you can pull back the canonical n plus 1 bundle over BUN plus 1 to BUN. And if you do that, so this is an exercise, you can see that you're going to get a copy of the canonical n-plane bundle over BUN plus a copy of a trivial complex line bundle over B. Now, C as a topological space, that's just R2. And so this map here, the map between this bundle and this bundle, gives a map on Thom spaces. But the Thom space of a bundle plus a trivial bundle is just the suspension by the dimension, the real dimension of that trivial bundle. So we get sigma 2 MUN, a map from sigma 2 MUN to MUN plus 1. Okay, and the map, so I'm missing a loops here. So W2n plus 1 is supposed to be a map from, you know, it's supposed to be a map from this to the loops on that. And it's just, I can take one of these copies and adjoint it over. Okay? And now for the even things, it's easy. It's sort of just manufactured. So you just take the adjoint to the identity map as you did for this. So that's the complex cobordism spectrum. It'll come back later. So if you're not comfortable with that, maybe until Thursday, you can sort of read up on complex cobordism. Okay, so now we have spaces. Usually we talk about their homotopy groups. So for spectra, we also talk about homotopy groups of the spectrum. And so we don't really want to like, so a spectrum is a sequence of spaces, and none of them, so they should all have equal dignity. And so the way that we do that is we define the rth homotopy group of a spectrum X, E, to be the colimit of the homotopy groups of its spaces. Okay. So the way that you get the maps in the colimit comes from the structure map in the spectrum. So those are going to be the homotopy groups of the spectrum. And a map of spectra is going to be a weak equivalence if it induces an isomorphism on homotopy groups. So this is the same language as the language we had for topological spaces. So let's see. Let's go for some examples. So the stable homotopy groups of spheres are going to be the homotopy groups of the sphere spectrum. Here I wrote this the sigma infinity because there was space for confusion. Okay. So often there's just, it's like, often we just put pi rs for that. That's common notation. And you can check, so the suspension spectrum, there was like a spectrification in there, but you can check that the homotopy groups actually are computed by this colect. So now let's see, we had our Eilenberg-MacLane spaces. So I was using G and I forgot to change this to G, so that was the notation we were using before. So pi star of this Eilenberg-MacLane spectrum, this HG that represented ordinary cohomology, that's just going to be one copy of G in degree star is equal to 0, and everywhere else it's going to be 0. So it really fits the description that you would want from something that you call Eilenberg-MacLane. Okay, so K-theory, the homotopy groups of K-theory, so I've described them as Z adjoint a class beta with its inverse. And beta is the bot class. So CP1, well, it's also, CP1 is the same thing as S2. Okay, so that's where you get the pi2 here. But it's got a line bundle on it, and beta is the class for the canonical line bundle. Okay. So what do I mean by this? Well, so it turns out, so we're going to talk about like smash products and symmetric mono products on things, and we're going to define ring objects, but K-theory is going to be a ring. So I've described its homotopy groups as a ring, as a graded ring, but roughly, so the 2R homotopy groups of K is a copy of Z on the class beta through the R, and the odd groups are 0. But in particular, this has negative homotopy. So Spectra can have negative homotopy groups. You took some kind of colimit, so eventually these numbers are all positive even if R is negative. All right, so similarly, pi star of mu, I described it as a graded ring. So it's going to be a polynomial algebra on classes xn, which are in degree 2n, and they're related to the Cobordism class of CPN. So they're not quite equal, but if you tensored with Q, then there'd be multiple of the classes for CPN. Okay? So in this notation, so pi naught of mu is Z on the unit, pi 1 is 0, pi 2 is Z on x1, pi 3 is 0, I didn't write it, and pi 4 has two copies of Z, one on x1 squared and one on x2. So remember this. This is going to come back. Well, so will this. Okay. All right. Okay. So now that we've defined our weak equivalences, so now I want to define something. So I'm going towards defining what people call the stable homotopy category. So I told you here's spectra, but there's a lot of different ways to talk about spectra, but it all gets it's all a means of talking about one category called the stable homotopy category. And all of the different ways to talk about spectra give you the same stable homotopy category. I'll say that again, but now first, before I can say what the stable homotopy category is, let's talk about homotopy categories in general. So suppose you have a category C and you have a subcategory W. And the subcategory W contains all of the isomorphisms in C. Okay, so in particular, it's going to contain all the objects because each object has an isomorphism from it to itself, the identity. And suppose you had two composable arrows F and G, and 2 out of these 3 arrows are in W, then so is the other. Okay. So suppose you have a setup like this, then the homotopy category, and then I'm going to say if it exists. Okay, so I'm not saying that it always exists, but if it does, then it's going to be a category, which I'll denote by homotopy category C comma W. It's a category but with a functor from C to that category, the homotopy category, with the following universal property. So suppose I have another functor. So I have a functor here, and it takes all of the elements of W to isomorphism. Okay. Then, okay, so I've got my canonical functor here. Then there's a unique factorization, FW. So it's unique up to unique isomorphism, okay, which is isomorphism of functors. And with the following, with the property that doing F is naturally isomorphic to, so there's a natural isomorphism, doing F to doing the composite iota and then FW. Okay. So basically any functor out of C that turns W into isomorphism factors through the homotopy category. Okay. So that seems, I mean, the description I feel is reasonable. The proving that it exists in general can be quite difficult. Okay. Sometimes it doesn't. Okay, so that's the homotopy category. So before we've talked about weak equivalences, right? We had the pi star, so these were the pi star isos, okay, on Spectra. So the stable homotopy category, and one way to describe it, it's the homotopy category of Spectra with respect to these weak equivalences. So any map that induces an isomorphism on homotopy groups becomes invertible in this category. So it exists. I'm not gonna talk to you about why and how, okay? So you can construct models. So instead of like going deep into like why it exists and how you get to it, I'm gonna just tell you about a list of its properties that are gonna be useful. And here I'm gonna ask that you make a leap of faith. So I only have 4 hours. So at this point, I'm gonna ask that you sort of take SH for granted with the following properties. You know, on your own time, you can read more about it, or you can just, for this course, you can work with it axiomatically.
Hi, and yes, this is Dan. Let me make a comment. Do you have a suggestion? You said about reading on your own time. Do you have a suggestion for audience members about a good reference for that? And also, you mentioned earlier about reading about MU. Do you have a reference, suggested references for that? Or maybe that might come later in an email or something if you can't think of something right now.
No, so for MU, maybe I want to think about it, but for SH, I suggest Margolis. So I'm just gonna write Margolis because in the link that I shared, there's a link to that will lead you to finding this book. Okay, so in the link that I shared on my website, there's a bunch of references, and the one for Margolis, you can look in there, and it talks about the stable homotopy category from this sort of axiomatic point of view. So that's one place. I'm sure there are other places. So maybe we can like open a chat for people to suggest other places that they like to read about this stuff. But that's the one I found. For MU, let me think about where the most efficient place to read. I'll get back to you. Okay. You can certainly read about MU in the parts of MU that I'm going to use in. So there's on that website, there's Ravenel's book. So this is the one it's the orange book. So nilpotence and stable homotopy theory or something. Okay, and then there's a lot of the stuff. So if there was a main reference for what I'm doing during this course, I would pick this book of Docs. All right. Okay, so what's the stable homotopy category? So this means like usually this is a notation we use for like HOMs in a category. So usually we write it as brackets XY, okay? So it reminds one of homotopy classes of maps. One has to be careful, it's not always. So you can define homotopy classes of maps in Spectra. It's not always computed like that. So, you know, you can be too naive, but in this talk, XY will be the HOMs in the stable homotopy category. So by definition, they're the right thing. Okay, so the category is stable. So the finite products and coproducts are equivalent in SH. So like, for example, if you have a diagram like this, and suppose that it's a pullback, then it's also a push out. Okay. So it's a closed symmetric monodal category, and the unit is the sphere spectrum. Okay, the smash product, the symmetric monodal product, people often denote it as a smash product. In recent literature, people also just write it as a tensor. Okay, and so being closed means that there's an internal HOM object. So you know, there's the mapping space between two spaces. Well, there's the function spectra between two spectra, and that's what people denote it by. Okay, and so close, I mean, in the close is that there is an adjunction like this. So maps from x smash y to z is isomorphic to map from x to the functions from y to z. Okay. So let me just say, like in our previous model, if you had, so suppose that you had, oops, that's not the pen I want. Okay. Suppose you had sigma infinity x smash with some spectrum, then you could, so the n space of that, you could think of as x smash with the n space of E, okay? But you'd have to sort of spectrify, okay? So if you're just smashing with a suspension spectrum, it's easier to think about it. So it's a triangulated category. So again, so you can read about what that means more in this Margolis reference or on the internet. But it means, so in particular, there's an endofunctor. So there's an isomorphism of the category, which is called sigma, and it can be described as smashing with S1, just like you would in spaces. But it's an invertible functor, so its inverse is actually the function spectrum from S1 to X, and this is what you think of usually as loops on X. Okay. So in spaces, loops and suspension are not inverse of each other. They form an adjunction. But in spectra, once you stabilize, once you go to you go to suspension spectra and then you put that in the stable homotopy category, they actually become inverses of one another. So now it's a triangulated category. So in a triangulated category, there are distinguished triangles. And in the stable homotopy category, the distinguished triangles are the cofiber sequences. Okay, so this is a cofiber sequence. So if you have a map F from X to Y, then CF, so it's the same picture as when you did in spaces. So maybe you had X, it went to Y, and then the cofiber was the thing where you just coned it off. Okay, so this is CF. And in fact, you can do the same type of construction in spectra. Okay, so it's like Y, and then you join a cone on top of the image of X. So let me just say, I didn't write it on the slide, but why cofibers, why not fibers? Well, so because of this, fibers and cofiber sequences are going to be the same. So you could have said that the distinguished triangles were the fiber sequences too. Okay. And now you get, okay, so if you have a distinguished triangle, then they give long exact sequences. So if you take a distinguished triangle and you apply either of these things, you get, I don't know if I said it, but you get abelian groups. So you can talk about long exact sequences. And you get those from applying these functors to distinguished triangles. And in particular, if you take this one and you take Z to be the sphere, then you get a long exact sequence on homotopy groups. So that's the stable homotopy category, or some things about the stable homotopy category. I'm sure there's more that I could have said, but I've picked this list of things to say. All right. So there are many models for spectra. So there's EKMM or S modules. So Elmander, Krish, Mendel, May. There's symmetric spectra. So here, so I guess Shipley and Smith, there's so here I don't know, maybe add May's name wherever necessary, orthogonal spectra, and then there's like ways to go at this from the infinity category perspective. Okay, so pick your model. So what do I mean by model? So there's other choices of categories with weak equivalents whose homotopy category will give you the stable homotopy category. And in particular, there are models. So I said that the SH was symmetric monoidal. Well, so the model I gave you, it's hard to, you're not going to put an actual symmetric monoidal product on that model. So like an honest one, but there are closed symmetric monoidal models. And I'll just use, from now on, I'll just assume we have spectra with everything that we want, and and go from there. Okay. Okay. So that's spectra. I need one more definition before I move to the next topic. So homology and cohomology. Now, we started the lecture with cohomology, and we said that cohomologies are represented by spectra. Now, if you have a spectrum, then you get a homology and a cohomology functor. And remember, you can take spaces, take the suspension spectrum, and put them in the stable homotopy category. So now I'll describe these as functors from the stable homotopy category to abelian groups. Okay? And the homology is you take X and you send it to the nth. So for the nth homology group, you send it to the nth homotopy group of E smash X. And for cohomology, you take X and then you send it to the minus nth homotopy group of functions from X to E. Okay? So there's a clear duality between these two things, or like sort of dichotomy, or whatever word you want to use. And it turns out that this is, so if E was a spectrum, so this is the maps in the stable homotopy category from X to the nth suspension of E. So here, when I say that, I mean like you use that shift functor, okay, from the triangulation. And then common notation is E sub n is the reduced homology of the sphere. That's the definition. It's by definition, it's pi n of E. You can also see that it's going to be the minus n homology group of the spheres, and we call this group E minus n. Okay, so this is notation that people say to just declutter things. Okay. Okay, and so the stable homotopy groups. So if you have, okay, so I guess I didn't define these. So if you have a space, X is now a space. The stable homotopy groups of X is going to be the colimit n plus R of pi n of X. Okay, oh, this should be R. Okay. So it turns out that once you put X into spectra and you think of stable homotopy groups, it's actually a homology theory. Okay, so it's the homology that the sphere represents. Okay, so it's the reduced homology of X is going to be pi star of X, and if you had the suspension spectrum, that'd be the stable homotopy groups of X. Okay, and remember the weak equivalences, they were pi star isos, but pi star isos are just the same as S naught homology isomorphism, and SH is obtained from spectra by inverting these isomorphisms. So why, so the next topic is, well, we chose to invert the weak equivalences, but we could have also inverted other isomorphisms for other homology theories. And that brings us to the topic of Bousfield localization. Okay? So a map F is going to be an E equivalence if it's an E star isomorphism. Okay, so it's the same as weak equivalences, except that you replace the sphere spectrum with a spectrum E. Okay, you can look at the subcategory of spectra, which contains all the E equivalences, and that's going to satisfy the conditions that we had before for a homotopy category, for constructing the homotopy category, and we're going to let SH sub E be the homotopy category spectra when you invert the E equivalence. So so we'll see below, this is what people call by the E local stable homotopy category. Okay. Now it's a theorem of Bousfield. So, and the paper of Bousfield is on my website. Okay, it's a theorem of Bousfield that this exists. Okay. In fact, so I'm going to sort of need a little bit more later about these things. So we're going to say that X is E acyclic if it doesn't have any E homology. And we're going to say that Y is E local if all of the maps from X to Y are 0 whenever Y is E acyclics. Okay, so E local doesn't see E acyclics. So they're kind of like orthogonal to one another in the category, in the stable homotopy category. Okay, so now for whatever model of spectra you have, let's let SPE be the full subcategory whose objects are the E local spectra. And in fact, the SHE, the e-localization of SH, is going to be the homotopy category of e-local spectra, but where you invert the weak equivalences between e-local spectra. Okay. And here I have an exercise. So you might have to like spend more time thinking about what the concepts I just introduced, the definitions. But from the definitions, you should be able to prove that a map between e-local spectra, so X and Y are e-local because they're in there, is going to be a weak equivalence, so a pi star isomorphism, if and only if it's an e-equivalence. Okay, so between e-local spectra, the weak equivalences that we're interested in the stable homotopy category are sort of detected by E-star homology. So you can use E-star homology to tell when two things that are e-local are actually weakly equivalent. Okay.
Yes.
Yeah.
How much should we be reading into the word local? I mean, is this sort of purely in like an algebraic sense, or is there also some topological interpretation of locality here?
So probably all of the above. So there's definitely analogies with algebra. So you can construct localization more generally than here. Okay, so you just invert certain isomorphism, and so the sort of prototypical example is if you have a ring and you have a prime ideal and you localize the ring at the prime ideal. So that's or like if you have like a scheme and you invert, so if you want to look at an open set, which is a neighborhood, which is kind of a local thing, you invert something, that's a localization. So it's all part of that language. So maybe can I leave it at that?
Sure, yeah.
Okay. All right, that was Josh, right?
Yeah.
All right. Okay, so what's the universal property of localization? So I'm going to make one more definition. An e-localization is going to be an e-equivalence from X to LEX. So in particular, this is an this is an E star iso, okay? And this thing is local, okay? So you just like replace X by something that's e-local, but E star doesn't see the difference between X and that thing. So again, theorem of Bousfield, they exist and they're unique in the stable homotopy category, so up to weak equivalence. And because of this, you get a functor from SH to itself, but its image is going to be in SHE. Maybe that's not right. Let me just write that was a different category. Okay, so sorry, it's going to go SH to itself. And there's going to be this eta here, these localization, it gives a natural transformation from the identity to the functor LE. Okay. Now, okay, so this LE has the following universal property. If you have a map from X to Y with Y, an e-local spectrum, then there's going to be a unique NSH. So the uniqueness is up to homotopy, so it's in SH. There's going to be a unique map here that factors F, okay? So X maps to an e-local thing, then actually you can sort of think of that as a map from the e-localization of X to Y. And in fact, so if you take so this map here fits into a distinguished triangle because all maps do. And so this would be, so if I wrote it as a distinguished triangle, I would do this, okay? And this term here in this distinguished triangle is actually E star acyclic. So its E homology is going to be 0. And it's going to be the terminal E acyclic spectrum with a map to X. So this is the initial E local thing, and this is the terminal E acyclic thing. Okay. And I think I've given you enough information to do the following exercise. So again, you might have to sort of first absorb a little bit, but suppose that I take, so if I take, so the wedge is the coproduct in the category of spectrum, so maybe I didn't give you enough information, I forgot to say that, okay? So if you have F wedge E, you can think that's a homology theory, that's a spectrum, the coproduct of F and E gives a new spectrum, F wedge E, and there's always going to be a natural transformation from this to this, from this localization functor to that localization functor, and in fact, you have these equivalences. I really like to read about this stuff in Ravenel. So the orange book, so it's nilpotence. And there's a chapter called Bousfield Localization. And somehow, I don't know, everybody has their go-to references. That's my go-to reference. That's where I get the information I need when I need it, usually. Okay. All right. So let's do some examples. So localization. So I call this slide Localization and Completion because, so you have a feel, if you've done enough algebra, you have a feeling of what completion means, and you have a feeling of what localization means, and this Bousfield localization construction captures both. Okay, so G is going to be an abelian group, and SG is going to be a Moore spectrum. So you can construct it as, so you pick a presentation of the group. So I didn't write it as such, but that's an exact sequence. And then for each generator in the relations, you take a sphere, and same for each generator for each generator. And then you take the coproduct of all these, you map into that, and then the cofiber is SG. So this thing is a distinguished triangle. So this is the cofiber. Okay, so that's one description of a Moore spectrum. Okay, so now if G is the p local integers or the rationals, then it turns out that Bousfield localization at this Moore spectrum is just you take SG and you smash it with X, okay? So very simple to describe. And the homotopy groups of the localization is just gonna be you take pi star of X and you tensor with G, okay? So now that should sort of remind you, in a lot of cases, that's what you do when you p localize. Suppose you take a ring and you wanna localize it at P, then I guess maybe you need some finite generation hypothesis or something, but you can usually tensor with C localized at P, okay? All right, so the P, so now this is a definition. The P localization of X is gonna be denoted X sub brackets P, and it's this localization. The rationalization of X is X sub Q, and it's that localization, okay? Okay, so that's for like the usual like localize at a prime P type thing. Now, if the groups pi star are finitely generated, you can also describe completion in such a way. So completion, so I'll skip to here. The completion of X, so that's a definition. The P completion of X is going to be X sub P, no brackets. So that's annoying, but I'm going to stick to it. So with brackets, it's P local. This is P complete. And it's going to be the localization at that Moore spectrum. So the Moore spectrum for the Z mod P, okay? And if things are nice enough, then the homotopy groups are just, you take the homotopy groups of X and you tensor with ZP. ZP here is the p-adic integers, so it's the inverse limit of Z mod P to the I, okay? The p-adic integers, okay? So in these examples, sort of maybe you don't have a good way to sort of visualize. Well, here you do. You have a good way to visualize it. It's just like take a thing and smash it with another thing. And here you can recognize its homotopy groups, and you can actually write this thing as an inverse limit. So I'll point you to, this is in the Bousfield paper. It's well described. Okay. And I think these are all results of Bousfield. So that's localization and completion in the context of Bousfield localization. Okay. So these localization functors are going to be around for the rest of the lectures. So let's talk a little bit just about the sphere. So if you have, SP, that's the P local sphere by the definition we gave before, and it's this localization. And its homotopy groups are the P local integers. So these are the integers in Q whose denominator is not divisible by P. So I'll just stick to having said it. Okay. And in degrees bigger than 0, then you just take the P torsion, and so the P power torsion in the stable homotopy groups of sphere. So anything that's annihilated by some power of P. the rational sphere is easier. In degree 0, you just have Q, and in degree bigger than 0, you have 0, because the stable homotopy groups of spheres are finitely generated abelian groups, and they're finite if n is bigger than 0. So if you tensor with Q, you lose it all. Okay. Now,
and yes, this is Dan. What about the P completion of the sphere?
Yeah, so I didn't put it in, but it's put a ZP here. A copy of the p-adic integer. So this is for SP. You just the same story, except you put for SP you need a copy of the p-adic integers because the homotopy groups of spheres are finitely generated. Okay. So now if you have a connective spectra, then it turns out that the localization for this Morse spectrum is actually the same as the localization with respect to HD. This is the Allen Bird-McLean spectrum. So what does it mean to be connective? It means that the homotopy groups are 0 for r less than 0. Okay. And I think you just need to be bounded below for this to be true. I wrote connective, but I think as long as your homotopy groups are 0, for all small enough r's, then this holds. Okay. So in particular, like if I take the P complete sphere, that's L Z mod P. It's localization of, so these were as zeros. Okay. Sorry about that. All right. So in a lot of cases, this localization is very familiar also. Okay. So now I want to talk about K-theoretic localization. So now I'm gonna maybe here this is gonna like step up a level of the kind of background I need. Okay, so I need some. So I'm gonna assume some familiarity with the Adams operation. So if you have K-theory now, there's just like I guess I didn't even need the star. You just have your regular. No, I guess that's right. So you have your regular K-theory, like classifies vector bundles. Then there's these operations which go from K star of X to K star of X, CK. They're unstable, which means they don't commute with the suspension. Okay. But you can look in, so this is in Adams' Blue Book, and I don't have the page right now, but in the Blue Book, and that's not on my website, I'll put it. Okay, you can read about how suppose that these operations, they're gonna, if you take P complete K theory, just like P complete as in the previous slide, then for any p-adic integers, these operations are gonna give rise to stable operations on P complete K theory. Okay, so sorry, I didn't mean any, I meant like any p-adic unit. Okay. So you have these unstable operations. They're not that great, but once you P complete, so anything that's not 0 becomes a unit in the. Oh, sorry, that's not true. So for any integer in the p-adic numbers that's a unit, you actually can use these guys to construct the stable Adams operation on P complete K theory. Now these might seem mysterious, but let me just tell you what they do on pi star. So pi star KP is the p-adic integers adjoin the Bott class. Okay, so all I did was tensor with the p-adic integers. Okay, and the kth Adams operation just multiplies beta by k. Remember, k is a p-adic unit, so it's in the coefficient ring, and that's it. And so that tells you what it does on pi 2, but they're ring homomorphism. Okay. So they act by ring. They're like better. They're ZP algebra homomorphisms. Okay. So that determines all. So not so hard to describe on homotopy groups. All right. So now let's describe the K-theory localization. So here I'm picking P to be odd for this story. I could tell a different story for P is equal to 2, but it would be more complicated. So I'm going to stick to P odd. Okay. So KZP. It's mod P K theory is going to be K smash this Morse spectrum for Z mod P. Okay, so its homotopy groups are just Z mod P adjoin V1 plus or minus 1. Okay, so you can compute that using the long exact sequence on homotopy groups. Sorry, that's wrong. That's beta. Okay. Okay, so here's so this is a theorem. So I'm going to say Adams, Baird. Okay, so this is something that I'm just going to throw a lot of names. So it's sort of the way we say this theorem now, but it's sort of it's the work of, it's a bunch of little pieces that you put together, and now modernly you can sort of phrase it and it looks nice, but it's the work of at least these people, if not at most. Okay, so and the statement is that, okay, so there's a distinguished triangle, so a co-fiber sequence. So you take P-complete K theory, and then, okay, so L is going to be a topological of the p-adic units. So this is, so you can, this thing here is isomorphic to CP minus 1 times a copy of the p-adic integers. And it turns out you can take one element whose like all the powers it generates is dense in CP cross, okay? So take one of these. And then you take the Adams operation for that L minus 1 on P-complete K theory. And the fiber or co-fiber, depending on how you want to think about it, is the P localization, is the, sorry, the K mod P localization of S naught. Okay. So again, this is a localization. This one is a lot less intuitive. But with, if you have this fiber sequence in hand, it's not so bad to compute pi star of LK Z mod P of S naught. So if you have, so you use this and the long exact sequence on homotopy groups associated to that, and you can compute them. All right, so what is that? That's related to something that you might know. So it's related to the image of J. So by Bott periodicity, the homotopy groups of the, so the union of all the orthogonal groups is just a Z in degrees 3 mod 4. And there's a homomorphism, so you can read about this in a lot of places, but in Hatcher's vector bundles notes, for example. Okay. And if you look at the image in these degrees, it's these groups, they look nasty, but if you just look at the P components, so the P order subgroup of all of these abelian groups, then things look a lot nicer. So what does this mean? So this means that in pi 3, it's a Z mod 3. It's the Z mod 3 and Z mod 24, okay? That's a Z mod 8, it's the Z mod 8 and Z mod 24. So it's nice and regular. So an exercise, which, I mean, I don't know, I guess it could be tricky, but is to compute the homotopy groups of this thing using the techniques I told you on the other slide and compare with the P component of the image of J, and you will find that they agree in positive degrees. Okay? So that this thing detects the image of J. Okay, so next time, we're gonna fix a prime P. And we've talked about generalized cohomology theories, but we haven't talked about nearly about as many as we will. So we're gonna talk about spectra, one for each integer and one for infinity, called the Murabba-K theories. The localization at their wedge is gonna be called, is just what people call ln of x. In fact, you've seen, we've already talked about a bunch of these localizations. And we'll come back to this, but there's an amazing theorem of Hopkins and Ravenel called the chromatic convergence theorem. And it states that the P local sphere is actually the inverse limit. So this is the homotopy inverse limit, so in SH, of these ln local sphere. And this is what people call the nth chromatic layer. And what is chromatic homotopy theory? It studies the P local sphere via this chromatic filtration. I'm out of time, so I won't be able to do the cool slides, but I'll do them next time. But I would like to say thank you.
Okay, I'm gonna unmute everyone so we can thank her. Let's thank her. Okay, and I've just muted everyone again to cut down the background noise. Do we have any questions for Agnes right now? Okay, okay, go ahead.
Do you have a conceptual explanation for why, for connective spectra, P completing is the same as localizing at a H Z1P?
Me right now, no, but I think if you read the paper on Bousfield, I think you'll find what you want.
Thanks.
Like the part in like just open the paper that's on in Bousfield. Like I'm sure there's a good answer. I don't have it, but I'm sure you'll find like satisfactory. It's it's a beautiful paper. It's very simple. I mean, I don't mean that in a bad way. I mean that in a good, like, you know, well written. Yeah.
Other questions?
Hey, I had a quick question.
Go ahead.
Go ahead.
Can you hear me? Sorry. Well, assuming you can, you said earlier in the slides that the homotopy limit and colimit was happening in SH, that was actual limit and colimit in SH. I was curious if you had an explanation for why those two agreed.
So that's the definition of the homotopy colimit. So I mean, you could the homotopy colimit is the homotopy meaningful colimit. So you can think of, it's like if you're going to go in SH, that's like what is the homotopy colimit? It's a construction in the so you want to take like the homotopy category of something, these homotopy things, their construction in the original category that gives you the right answer in the homotopy category.
Right, but I thought that they didn't always agree with the limits and colimits in the homotopy category. I thought they were just the.
Oh, I could, okay, so I could have been wrong there. So I'm gonna withhold my. Maybe I'll take my statement. I guess I don't know. I'm not good enough at that stuff to answer your question, I think. But isn't Dan in the audience? Duggar?
Which Dan? Yeah, Dan Duggar's here.
Maybe Dan can.
Yeah, I'm here, and it's not the naive limit and the stable homotopy category. So those are different things.
Say that again.
You're correct that the exact statement that you wrote is not correct in the sense that it is not the naive limit in the stable homotopy category, right? It's the limit in the infinity category.
Okay, all right. Okay, so let's make that the statement.
Thank you very much.
Thanks, Dan.
Okay, other questions? Okay, I'll unmute everyone one last time so we can thank her again. All right, that's it for today, and we'll see you again on Thursday for part 2 of the series. Thanks, everyone.